Hi, everyone. Welcome. My name is Lyle Tavernier,
I'm Brandon Rodriguez.
and today we're going to be talking about Mars rovers, and we're going to be talking about how we design wheels for specific terrains and how we can improve those designs as we learn more and more about how those work. So we'll take Q&A afterward. We're also going to have a little opportunity to build with Brandon. We've got a cardboard rover that you're going to build and then improve the design upon. So if you have those materials, fantastic. If you don't have them, you can follow along and build them later. So the first thing we're going to do is talk a little bit about some rover history. So the first thing I want to do is show you this rover here. This is the very first rover that we ever sent to Mars. It is the, whoop, I guess that didn't stay up for very long. Let me try that again. Let's bring that one back up. Here we go. All right, so this is the very first rover that we sent to Mars. This is the Sojourner rover, and it wasn't very big. It was about the size of a microwave oven. So you can imagine those wheels that you see there weren't very big. They had about the diameter of a bagel, so not too big, but really we just wanted to see if we could drive around on Mars. And sure enough, we could. This is a picture we took from the lander, pointed at the rover, and this told us that sure enough, we could in fact drive on Mars. Now, it's kind of hard to see in there, but the wheel itself has a lot of little spikes on it. And that was so that as we were driving, we could sort of grab into whatever terrain we might be driving on. There were a lot of unknowns about where we would be landing. But there were also, they were sort of sticking out so they could act like little paddles, almost like digging into the sand. So that's one way that we drove around. Now, scientists realized, oh, we want to build a bigger and better rover to do more capable things. And so engineers had to design a bigger rover that had different wheels that were able to go much further. And so if you take a look at this picture, you can see this is a computer illustration of the Spirit and Opportunity rovers. These were much, much bigger. They were about the size of a golf cart. So you can imagine those wheels were also quite a bit bigger. And I'll show another picture here. This picture right here, you can kind of get a closer look at those wheels. Again, the terrain on Mars is kind of unknown depending on where we're going. We do know that there's a lot of rock on Mars. We know there's sand. We know that there's a lot of dirt, but we really do need to design things that are capable of driving in a lot of different conditions. Just like if you're driving in the snow, you might need snow tires or snow chains, versus if you're just driving on dry pavement, it's going to be a little bit different. So lots and lots of miles went onto these. I think Opportunity did 26 miles on Mars, over 26 miles.
Did a marathon.
Yeah. So what that meant is that when we built another rover, the Curiosity rover, we had designed even bigger wheels. And so here is a sketch of the design. And this is much, much bigger. It's about the size of a small SUV, about 7 feet tall, 10 feet long. So those wheels, again, are going to be very much, very, very large compared to the other wheels. So Brandon actually has one of these wheels here that he's going to pull up. This is a model wheel that you can see just how big it is. So compared to the very first one that I talked about, what did I say? A bagel?
A bagel.
Yeah. So not nearly big enough for a giant rover like the Curiosity rover. And you can see we've got some different tread designs here. These tread designs were made to sort of grip onto rocks as the rover was driving over them, but also provide a little traction or friction as it was driving through different, maybe looser materials like sand or loose dirt. We've also got different, what we call struts inside the wheel compared to those other wheels too. So quite a few changes here, but Brandon, there was a problem with these wheels, right?
Right. So even though we test the wheels, over and over and over again, and they're made of, very, very strong material, aluminum on the outside, titanium on the inside. Each one weighs about 40 pounds. The presence of these chevron-shaped grousers, they're called, grousers go out, tread goes in, actually cause some of the rock structures to get caught. So if you can imagine, if I were driving over a rock, I kind of force it into these divots here, and that in the end causes the rock to pierce through the wheel. So eventually these wheels started getting more and more damage.
And I've got a picture that I'm going to show of the actual wheels on Mars. You can see holes actually punch through the aluminum wheels. And so over time, we realized this could cause some pretty serious problems. So we changed the way we drove until we understood the problem better. But because we knew that we were going to be building a new rover, the Perseverance rover, we needed to come up with a better wheel design. And so the picture that I'll show you now kind of shows you a side-by-side comparison of these two different wheels. So the Curiosity wheel on the right, the Perseverance wheel on the left. My image is switched, so hopefully I said that right. It might actually be the other way around. But you'll notice the Curiosity wheel has those grousers. The Perseverance wheel has a much smoother tread on it. I guess not tread, as Brandon said, a tread goes into the wheel, a grouser goes out. It's not perfectly straight. There's a little bit of a wave to it if you look closely. But again, this was a wheel change that was thought out and very meticulously tested to make sure that it was going to do what it needed to do. And so far, over a year, has it been a year? A Martian year, a Martian year, almost a Martian year, in what, just a couple of weeks in February. So a lot of design went into this, and we were pretty successful. And so that's kind of where we're going to now talk about how you can take a design that exists and improve it. So we are going to build a cardboard rover. Brandon, I don't know if you want to talk about that process now or jump right into the build, or what are you thinking?
Yeah, I guess I'll say very quickly that before we get started, the body of the rover is what we actually want to keep static here. We want to keep that the same. So even though from Curiosity to Perseverance, many technological updates were made, and it's so much more modern and complex, the focus of today is to kind of have the same rover body, but really iterate just the wheel design. So what we'll do is really focus on just the wheels and see if we can kind of make our iterative improvements from there. So what you can see is the materials you guys will need for this lesson. And we may, we're going to kind of just set it up for you as getting the body and basic structure complete. And then we'll turn it over to you guys to kind of really do your testing on your own time. But the key is to start with one piece of cardboard here that's going to serve as our chassis. So I've got just, a small square of cardboard, and you guys can cut this to be long or short. But if you kind of take the corrugated sides here, you can see the direction of corrugation. I'm just going to fold this up into like roughly thirds, like so. And as such, I've got kind of a box car, if you will, right? From here, what I want to do is very, very carefully, I'm going to take my scissors and I'm just going to poke a hole through each side. You got younger students, maybe you want to help your students out with this or use more child-safe scissors than the ones I have. Hopefully I demonstrate safety here and do not hurt myself. One down, pretty good. Two down, thank goodness, on a recorded line. But you can see I've got a hole here that's just wide enough effectively for me to stick a pencil through. And this pencil is going to serve as the axle on my rover. There we go. Like so. So I want to make sure that this is loose enough that it can turn, because as my rear axle, this is where I'm going to fix my wheels. And for my wheels, what I have is I'm starting with just two smaller squares of cardboard here. Now, spoiler alert, square is not a great shape for a wheel. So even though I'm going to fix on these square wheels, I'm going to trust you guys to make a more improved shape than this. In order to get these attached, depending on what shape you want to make, you might want to first find the center of your wheel so that you can effectively make sure that you have a point for where to put a puncture, so that you don't have kind of an off-center wheel that doesn't roll correctly. Now, again, here, I trust you guys to cut any shape you like. I'm going to keep mine square. Once again, I'm going to kind of safely poke a little hole through here, like so. I'm going to do the same on the next one. Use the same one as a template. And sure enough, now I can attach my wheels, like so. as you can see here, I've got kind of the makings of a rover. Probably not going to go very far with these wheels. And what I'm going to do is I'm going to add a little bit of a energy system here so that I can allow this to move forward. The way I'm going to do that is with a couple of rubber bands. You can see here. These guys are a little too short to span the entire length of my car, of my rover here. So what I'm going to do is I'm going to tie them together. And here's the magic trick that I learned from my good buddy Lyle. If you have one kind of hanging on the other, and then you kind of tuck it through like you're tying your shoe, like so. Look at that. That's why he gets paid the big bucks, right? Now I have a little bit of length here. And similarly, on the back of my rover, I want to kind of tie this on just through the loop. Try to do this nice and slow, right? Just like that. And now I have a rubber band tied to my rear axle, right? So my next step is to kind of fix this to the front here. And I do that by just cutting 2 little slits, just like this. And I'm going to stretch this on to those slits, like so. Okay, so let's kind of a quick recap since we went through this real quick. My first step, I want to take a piece of cardboard. I want to fold it up into thirds, like so. And again, if you want, you can cut yours to be short or long. Doesn't matter. It could be thicker here, right? I kind of did roughly thirds, but you don't need to. I poke these little holes for my rear axle in the back. That rear axle is a pencil, which goes through here. Like so. My nice square wheels in much need of optimization. They're going to go on the back. Like so. And then I tie my rubber band onto this side. Like so. And stretch it to 2 slits right here on the front. Cool. And again, I'm going pretty fast. It's okay if you guys need some time to catch up. You'll have plenty of time to do this and to make some revisions. The last thing I really need is to put a front axle on. And for the purpose of this experiment, I really only need the rear axle to have power. So what I'm going to do is just take a simple drinking straw, turn my rover over here, and tape it underneath, right? So if I do that quickly, like so. I've got a front axle now, and I really don't care about my front wheels for this experiment. So what I did is I just got a couple little mints, little round circle mints. Teachers, I highly recommend not to use lifesavers because they get sticky and gross, and that's how you get ants. So instead, nice mint is probably your best way. And these wheels can roll pretty easily on the front on the width of a straw, no problem. Okay. Lastly, before I turn it back to Lyle, once you have your wheels made, the means to get this thing to power up is the old school kind of like cars that you rolled back and charged up, and I can get that rubber band to charge. So if I roll this up, you can see the rubber band gets caught, and if I let go, it's going to give, right? Now I can already see I've got some problems on my design, right? I encourage you guys to try, probably make a few mistakes and see what's going on. But even looking at this, you know, I've got a couple of hints for you right here on what could possibly be a flaw in my design. I've got some work to do, but it's a good first start. So I'm going to let Lyle show you one of his completed ones, and we'll kind of go from there.
Great, thanks, Brandon. So I have here in front of me one that I already built. It's not complete. It actually doesn't have the rubber band in here. because there was something that I wanted to talk about, and Brandon mentioned one of the many potential challenges you might encounter are the actual spinning of the wheels. So what I like to do, even before I try figuring out my wheel design, is just make sure that I can actually spin them, because my cardboard, if it's too far in, it really pinches that and now it doesn't spin. Same thing if it's too far wide, it doesn't spin as well either. So you want to find how to make this just kind of the right shape. And I won't say that I cheated, but I kind of came up with a way to solve my problem. Is I put a little piece of tape here to hold these two sidewalls where they're supposed to be. And that really helps me get that cardboard set up in just the way that it's not putting too much pressure on my axle, and so they spin nicely. And I'm not going to turn this to the side because I don't want you to see my wheel design. But the truth is, my wheel design might not be the same wheel design that is best for the surface that you are driving on. So for example, here on the floor, we have very slick tile. And right here on the tabletop, it's kind of rough and textured. But if you have carpet, either at home or in the classroom, you're going to use different wheel designs. So check out the different, or well, think about the different materials that you're driving on, and then think about what the best maybe tread or grouser design you might want to put into your wheel. And then one thing that I always like to remind people, because this is a mistake I make, is once you cut off, you can't put back on. So be sort of considerate about what you're cutting, and don't cut too much unless you have lots and lots of cardboard squares that you can then go get more extra wheels. But if you only have the 2 cardboard squares, then maybe be a little bit more considerate about how much you're cutting off with each design change. So yeah, I hope that you come up with a good design that works well. It is a challenge. We don't call it the cardboard rover challenge for no reason at all. It actually is a challenge. It's difficult to do, but with enough work and enough effort and trying different designs, we think that you can do a pretty good job of doing that. So Brandon, thank you so much for showing that. What I want to do is, before we take questions, I want to show a video of how we test driving the rover here before we send it to Mars. Again, we have to make sure everything works perfectly before we send something to Mars. So what I have here is the very first test drive of the Perseverance rover. And before I hit play, you'll notice it has those smooth grousers on the wheel, but it looks very similar to the wheel that Brandon was holding up in the middle. It's got a very similar strut design in the middle. So I'll go ahead and hit play, and you can see that as the rover moves, we're checking very closely to make sure it's doing everything that it is supposed to do. You'll notice there are a lot of people checking it out, and you'll also notice it's not going very fast. So while we finish this up, if you've got questions, now's the time to put them into the chat, and we will try to answer the questions as best we can. So I'll let this keep going for a little bit because it's just kind of neat to watch it go. But once it is over, we'll be ready to answer some questions. Now you'll notice we have to test to make sure it can go over angled slopes. This is capable of climbing over pretty big rocks, but we don't want to do that in the clean room while we're trying to just test to make sure that it can actually drive.
And as you guys are putting questions in, feel free to ask both about how we've built rovers in the past. It can be about science, or it can be about your design. You guys just need a tip from a pro. We've done this a few times. We're happy to give you guys a few clues as well as you're working.
I realize we gave everyone a task to build a rover and come up with a design, and then started asking them for questions. So you're probably hard at work. Yeah. So sorry about that, but feel free to take a minute and think about things you may be curious. So I do see a question, and one of the questions is, what are the wheels made of? I know you had mentioned titanium, but I was busy looking up a picture, so I didn't hear quite everything that you said. And there were some people who came in late who may have missed that too.
Yeah. The wheel design is really wild when you think about the materials that need to be used for something like this. First of all, you can't go to the store and buy these, right? There's no, going to AutoZone and picking up a wheel. These have to be made in-house. And that means that we get effectively the raw materials, just blocks of metal, and carve out the wheels from a solid piece. We use a very lightweight but strong aluminum on the outside, and then titanium on the inside. Titanium also very light and very, very strong. The idea here being that if you can build something that's very strong, it'll survive, but it can't be so heavy that it's very difficult to launch, right? So getting off of Earth and to Mars is difficult enough. So you really want to make sure that you have something that is as lightweighted as possible.
All right, we've got some questions starting to come in. I like this first one from second graders at STEAM at Taupe Elementary. What happened to the first rover on Mars? So that very first one I showed you, Sojourner, very small test rover, it's still there. We don't have a way to bring rovers back. And to be honest, I wouldn't want to bring a rover back from Mars because we know everything there is to know about them. We built them. But the thing that I think is pretty interesting to bring back would be a rock. And that's actually something we're working on right now. Brandon, do you want to say something about the Mars sample return?
Sure. Yeah. One of the missions I'm really, really excited about. I think it presents a change in how space exploration takes place. When we talk about sending people versus sending robots, sending people to Mars is a very, very dangerous and complicated idea. However, what if we could send a series of rovers or robotic explorers to effectively mail back chunks of rock back to us here on Earth? So the rovers, for as advanced as they are and as incredible as the technology is, they'll still never compare to having all of the resources and time and energy of a combined laboratory here on Earth. So one of the kind of changes in philosophy is, what if instead we could shoot back a small bucket, a small cache of samples that the Perseverance rover has collected, and if they could be fired from a small rocket on Mars back to Earth, well, then we could open it and study it with all of our much more advanced resources here. So over the next 10, 15 years, we'll kind of see that come together. And with luck, we won't need to send people, right? We can actually just, do the analysis here, go get a cheeseburger on the way home, have a great day, not have to travel through space. I got a question here too about, it was how long did the rovers take to build? Now, I came in to JPL after Curiosity had landed, but I know that you were here for a lot more of it.
So I started here when Curiosity was still in the clean room, and it was only here for a few months before it had to go to the Kennedy Space Center for launch. But it took probably from the time that somebody said, hey, I've got an idea for building a really big rover to go to Mars, to the time that it actually landed on Mars was probably about 10 years. And shortly after Curiosity landed, someone said, well, let's start building another more capable rover. And that's where the idea for the Perseverance rover came up. And again, it was about 10 years from the time that idea came to when we actually landed on Mars for that rover. So it is a very long process. And some of you who, depending on what grade you're in right now, you may actually be able to finish high school, go to college, and either while you're in college as an intern or once you graduate as a scientist or engineer, work on the Mars sample return mission, which I think is pretty neat. In fact, one of our scientists right now, she came to JPL as a middle school student when Spirit and Opportunity landed, and now she is one of the lead scientists on the Curiosity rover mission, which I think is just such a neat story. So yeah, it takes a long time, but definitely worth the effort. So think about that as you're working on your rover design and coming up with maybe some obstacles that you have to overcome. All right, so let's take a look. I can't seem to find my mouse right now, so I can't move to the control questions.
Oh, here's a great one. What's the most important job on a rover?
Oh, well, I guess there's two ways to answer that. The most important job as far as a person operating the rover, or the most important job that the rover does?
Yeah, I think the maybe the latter is pretty cool to start with. Each of them has like a really critical objective.
Yeah. So I don't know that there's one job that you could say is the most important job that a rover does. But when we're designing missions, one of the things that we have to do is say, these are the goals and the objectives, the things we want to do on Mars. And that's really what drives or sort of gives direction to the rover itself. What are we going to do once we're there? And so, for example, the Spirit and Opportunity rovers, their job was to determine whether or not there was ever water on Mars. And they were equipped with instruments, scientific tools that would allow the scientists operating the rovers to figure out if there ever was water on Mars. And sure enough, there was water at one point in the past on Mars. So that meant the next rover, Curiosity, had a new set of objectives. We didn't need to tell whether or not it was once a wet planet. We already knew that. We needed the next step. So the next step for Curiosity was to determine or figure out whether or not Mars was ever habitable, meaning could it ever support life? And in order to do that, it needed to find 6 key ingredients. It doesn't matter if you remember what 6 they are, just remember there were 6. There were carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Brandon's a chemist. He knows those are pretty important.
Yeah.
Thank you. And sure enough, Curiosity found those ingredients for life. That doesn't mean that there was life, but that meant we were one step closer. So again, next step, Perseverance rover, new task. We're now looking for what we call biosignatures or signs of life on Mars. So we have instruments on board that can do that on Mars, but a big part of bringing those rocks back is to be able to inspect them more closely and with maybe a closer eye to see what's really there. So that's pretty exciting, the way that we step those responsibilities up for the rover.
Yeah, and this kind of leads into Teresa's question too about what are we hoping to see in the samples that get sent back. The Perseverance rover, again, as I mentioned, very, very advanced. However, it only has the tools that it got sent with, right? And it's running off an incredibly low amount of energy. As you saw, it drives very slowly, so it's not like we're covering a lot of ground every day. But you can imagine that if those samples that Lyle showed on the previous image, if they got sent back to us, that now we could utilize every single laboratory here. You got to imagine the rush for every scientist to get their hands on these samples and look inside these rock structures instead of just at the surface or kind of the mass of the sample. A lot of times, like for Curiosity, we drilled so the rock was crushed, and now we have like these nicely perfect cores, so we can actually see some depth and be able to see how the rock structure has changed over time. So we're getting a much more complete picture of the geology, of the history of Mars.
So here's a good question, because we're talking about rovers and driving, and everybody's working on their rover project to get it to drive on the surface. Why did the rover go so slow during the video?
Yeah, I think a lot of people are sad to see that we're not, speed racing and Tokyo drifting on this. But the rover goes very, very slow, very, very slow. I think it's a couple centimeters a minute, right? So a very, very slow rover. But again, we're not trying to get from A to B very quickly. We want to keep the rover safe. And the video you saw about the testing, that final mobility test was actually the result of a lot of testing, what we call the Mars yard. So we actually have a simulated Martian terrain that we built that looks just like Mars. We plant the rocks and we kind of drive over them and test. But you don't want to be driving over a bunch of rocks or get stuck in a ditch. You want this to be nice and slow and steady, because we only have the rover we sent, and we gotta protect it up there.
We probably have time for one last question. I don't know if there was one that you saw that you liked, but there's one here that I think a lot of people are curious about. How does the rover recharge? And how does it do it? So this is an important question, because it doesn't run on gas. It is an electric vehicle, but there are no charging stations on Mars either. So we have built-in batteries on the rover, but then there's a system that takes plutonium, not a whole lot of it, and it's a certain type of plutonium, but it's about maybe the size of my pinky, and it puts off a lot of heat. And there's a device on there that can take that heat and turn it into electricity, and that electricity then is used to charge the batteries. So we're able to run the rover with those batteries once they're charged up. And it doesn't put out a lot of power, maybe as much as a ceiling fan spinning around. So not a whole lot of power is generated. So we can't do everything all at once, but we do have a lot of capable instruments that can take turns doing the things that they need to do.
Yeah, not too far off from using rubber bands, actually.
Yeah, yep. Only a limited amount of power, and then once it's out, you've got to wind it back up and get it going again. So I think that's probably the last question that we have, but thank you so much for taking time with us today. We hope that you have some success with your rovers and come up with some good designs. And I'll hand it to Brandon in case there's anything else he would like to say.
No, I think really appreciate your guys' time today. Excited to see your final products. Have your teachers email us. Let's see how it went. We always appreciate feedback and seeing all of your genius designs. Every time we do this, there's always some cool new twist. And maybe we'll steal your idea for the next rover. So thank you so much for joining us, and I hope you have a great day. Take care. Bye, everyone.